Today we will talk about significant figures and scientific notation. Significant figures are important because they allow us to understand the precision of the measurements that we have. So, if you recall measuring liquid volume, we could use a beaker. So, a beaker, we could use a graduated cylinder, or we could use a pipette. Now, when we use these different types of instruments to measure out the liquid, what we immediately notice is a lot of times students will tell me, oh, the containers themselves are different sizes. Yes, but let's look a little closer. They are going to have markings on them to allow us to be able to know how much liquid is in that container. But if we compare the markings on a beaker to the markings on a graduated cylinder, although on the graduated cylinder they may also be spaced out similar to the beaker, the graduated cylinder is also going to have these smaller markings closer together. And so if we compare taking a measurement from these two instruments, then using the graduated cylinder allows us to measure more precisely. So if I am asking you to measure out a liquid, let's say that I want 10 milliliters of water, if I'm using a beaker, when you find that 10 milliliter line, assuming the beaker has a line for 10 milliliters, you don't really know if it's exactly 10 milliliters. I mean, it technically could be 9.8, maybe it's 10.0, maybe it's 10.1 or 10.3, because the beaker doesn't give you markings to know the difference between 10, 10.1, or 9.9, then you cannot tell me with that amount of precision how much liquid you have. You can tell me that you have about 10 milliliters because that's the closest mark you're going to be able to read in a beaker. If we look at a graduated cylinder, because those lines are closer together, then now we should be able to say that it's 10.0, 10.2, 9.9, all right? And then, of course, with the pipette, those markings are so tiny and close, we can be even more precise and perhaps measure, to the hundredths place with this particular instrument. So when we're talking about performing a calculation using our measured values, let's say that we used a graduated cylinder and we measured out 12.5 milliliters. Then we used a beaker to measure 10 milliliters. Now, as I've already explained, we don't know for certain if it's 10.1, 9.9, or 10.0. So if I ask you to combine these two liquids together, if we're adding these together, we can't say that we know for certain that we have 22.5 milliliters, or is it 22.7, or that's actually 22.3, because we only know that the 10 is about 10 milliliters and we don't know more precisely than that. Then when we combine those two values, our precision is limited by that 10 milliliter volume. So the least precise measurement that you are working with is going to limit how precise your final answer will be. So this is what we're going to keep in mind whenever we're performing our calculations in our class. When we perform a calculation using different variables, they're going to come with different amounts of precision. So when our math work is all said and done, we're going to take our answer and we're going to say, okay, well, the calculator may have given me this answer, but because of that number that I used for the mass, I can't really give my final answer with that much detail because I don't know for sure, because that mass wasn't provided with as much precision as the other values. So we're going to round it according to the least precise because that's all we can confidently answer with, okay? So Let's get to the rules for significant figures. Now, these are rules that are going to help us identify whether or not a value or a number is considered significant. So, all non-zeros are significant. Now, the wording on this is a little funny, but this is the common verbiage that we will see if we're looking at a textbook or even an online resource. But I want you to make sure that you comprehend what these rules are. So, by all means, rephrase them in your notes, rewrite them so that it's in a language that makes more sense to you. Okay, so perhaps you're not super comfortable with non-zeros. Hopefully we understand that it's any number that's not a zero, a non-zero. So this would be a number 1 through 9. Those are all going to be non-zeros. Okay, so numbers 1 through 9 are always going to count. Rule number 2 says zeros between other non-zeros are significant. So in other words, if a zero is sandwiched between other significant numbers, then by default it is also significant. So middle zeros, sandwich zeros, in between zeros, however you prefer to reference them. So we can see from the examples here, 50.3 has 3 sig figs. This is a non-zero, numbers 1 through 9, and so is my 3. So if the 5 is significant and the 3 is significant, since this 0 is sandwiched in the middle of those two, that also has to be considered significant. In the next example, 810101, these zeros are in between significant figures, so both of them are going to be counted as significant. Rule number 3 says zeros in front of non-zeros are not significant. So if we have a number that begins with a 0, those zeros will never count. All right, so they are always going to be insignificant. They will never be counted as significant figures. So we can see from this first example that we have 0.892. This first 0 is not considered a significant figure. It is in the front of the number, so leading zeros do not count for sig figs. So this will not be a significant figure, so we go to the next digit. That is a 1 through 9, so 8 is my first significant figure, and then these are all 1 through 9, so 3 sig figs in this particular example. If we look at the next example, 0.0035. Now, I know that there is a rule. It's the only one we have left, and we'll get to that in a second. There is a rule that addresses whether or not zeros are significant with a decimal, but this rule in particular, rule number 3, does not have any stipulations. Zeros at the front are never going to count. So when I look at this number, this is a leading 0. It is not significant. So we basically ignore that value at this moment when we're trying to identify our sig figs. So then that brings us to this 0, but it is also considered a leading 0. We have not gotten to a 1 through 9 yet. We have not found our first significant figure, so we're going to just keep moving through these zeros here at the front until we get to something that's a 1 through 9. So we have 3 zeros that are all considered leading zeros. None of them are going to count. 3 and 5 are the only 2 sig figs in this example, okay? Now, the very last rule says that zeros that are at the end of a number are significant only if the number contains a decimal. So here's where we have to learn the rule, and we have to learn when it is and when it is not. So far, our rules have told us rules number 1 and 2, this is when it is significant. Rule number 3, this is a situation where it's never significant. Rule number 4, we have to know more specifics about the situation in order to determine whether these are significant. So we're talking about numbers at zeros at the end of the number, so ending zeros. If there is a decimal anywhere in that number, we are going to count those zeros at the end as significant. So 57.00. This is an ending 0. There is a decimal point present, so it will count as a significant figure. Obviously, 5 and 7 are considered significant, which makes this 0 a middle 0. And rule number 2 tells us middle zeros are always going to be significant. So there are 4 sig figs in this particular number. 1200, the way that it is currently written, has no decimal point. So those ending zeros, this ending 0 is not considered significant, which means that this 0 is also not considered significant. So this particular number only has 2 sig figs, 1200. Now, if we were to take this number, 1200, and we were to say point, if I throw that decimal point at the end of the number, now this is an ending 0 with a decimal present. And so that would make all of these digits significant. So this particular example would have 4 sig figs because that ending decimal, or I'm sorry, that decimal makes those ending zeros significant. One last example I just want to put up here for you. If we have something like this, these are not considered significant. This is considered significant. Why? Because we had a decimal point up here. So ending zeros, if there is a decimal anywhere present in the number, will be considered significant. So now we have 3 sig figs in this example. Okay, so that's how significant figures work. So once we are able to look at a number and interpret how many significant figures are present, we're going to use that information to help us decide how to round our final answer for all math problems in this class. So there are technically different rules for determining the number of sig figs for a calculated answer using multiplication and division compared to a calculated answer using addition and subtraction. In this class, we are multiplying and dividing in every formula at some point. So I'm just setting the ground rule. We're going to be using multiplication and division rules for all calculated answers. And so the rule in this situation is that you take the values that you used in your calculation. You look to see how many significant figures are in each of the numbers that you used, and you're going to take the least number of significant figures. Again, this is what is limiting the precision of my calculated answer. So if I have 6.10, this has 3 significant figures. If I have 1.250, this has 4 significant figures. So when I put that in my calculator is going to spit out 7.625. So that is my calculated answer. But now I'm going to go back to my calculation and I'm going to say, well, I had 3 significant figures as the least number of sig figs. So now I've got to come to this calculated answer and I need to find 1, 2, 3 significant figures. So I'm going to chop it off here, but I'm actually not chopping it off. I always have to round whatever that last number is in my answer. If it's followed by something, I must round accordingly. So I have the 7 and the 6, which are not going to change. The 2 is followed by a 5. So I now need to decide whether that is going to stay a 2 or if it should be bumped up to a 3. Guys, if you just pretend that these numbers that we're dealing with are dollars, so if this is money, or if you pretend this is a situation regarding your average in a class, then you will magically know how to handle that particular number. All right, so let's just look at this for a second. If you had an average of 62.5, what would you get in a grade book? That would round to a 63. I am confident every student knows that that would round up, okay? So that's basically the rule. A 5 or greater is going to push it up to the next digit. 4 or less, it stays the same. So this is going to be written as 7.63. So when I am finalizing my answer, so whether I'm doing this on paper or I am typing this in to an answer field in Canvas, 7.63 is what my official final answer needs to be. Now let's look at this next example. I have the number 4 being multiplied by 2.25. If I put this in my calculator, I get a nice, pretty, perfect 9. Nothing else on my calculator screen to go with it. It's just a 9. Now, if we look at the number of sig figs, I have 1 sig fig and I have 2 sig figs. So according to our rule, the least number of significant figures is 1. My final answer should be 9. In my class, I have a special rule, and this is just something that we're going to do in my class. We are going to have a minimum of 2 significant figures, a minimum, which means every answer must have at least 2 sig figs. So although the answer is 9, and 9 would correctly be 1 sig fig, we are going to actually take that and we're going to bump it to represent 2 sig figs. So in this case, we simply would put 0.0 at the end, and that will give me 2 sig figs for my final answer. Now, sometimes my students ask, why do I have this rule? Honestly, guys, it comes down to when it's time for us to do our practice work, and I want you to see that change in a variable does or does not have an effect on your calculated answer. If we're only rounding to 1 sig fig, sometimes that final answer is not going to represent whether or not something has an effect accurately. And I want you to see that what we are doing, the calculations that we are performing, are real life concepts. It's real life application. I want you to see the value of it, and what you calculate should indeed match the factual information that you're receiving in class. So if we're only rounding to 1 sig fig and that's causing us to not see that changing this variable did indeed have an effect, that's a problem. So what I've decided is we're always going to show at least 2 significant figures, and then more often than not, we don't have any issues of calculating an answer so that we can recognize whether or not our variable affected the outcome. Okay, so that's the reason behind my rule. My students have dubbed this in the past the Espinosa rule because it's just special for Miss Espinosa's class. So I will remind you from time to time, the Espinosa rule says you need a minimum of 2. Okay? All right, now let's talk about scientific notation. Basically, we're just going to analyze the values that I have written here, and we're going to make sure we understand what all the parts of the scientific notation represent. So if I look on the left-hand side, these numbers right here are going to be written in what we would call standard form, just regular notation. If I look here, that's the left, sorry. If I look here on the right, these numbers are written in scientific notation. Now, this really should say 8 times 10 to the 6th as a superscript. When the file was uploaded onto the iPad, that font didn't transfer over properly. So I want you to understand that these are in scientific notation. This is not a multiplication problem. This is going to read 8 times 10 to the 6th. I also want to take a moment to tell you that whenever we're working electronically, there may be some programs or certain pieces of an electronic program or Canvas or some sort of document where the ability to create superscripts is not available. So you may actually see on a quiz or a test or a Canvas assignment or something that the number is printed like this, and that's just a limitation of creating special fonts on that particular program. So if you're unsure, if you're looking at something that's scientific notation, or if it's a math calculation, please ask for clarification. I will go ahead and tell you though, I do not use an X for the multiplication sign in anything that I have typed up, okay, because of the fact that it could be confused with being scientific notation, or it could be confused with being the letter X to represent an unknown variable. All right, so just a little bit of extra information there. Okay, so then let's look at what these numbers tell us about our value. Over here on the right hand side, I have 10 to the 6th for the first exponent, I have 10 to the 6th for the second exponent, and I have 10 to the negative 4 for the third exponent. Right now I just want to focus on the 6s and the 4. When we look at how the standard notation compares to the scientific notation, we probably very quickly recognize that our decimal is in a different place on the standard side compared to the scientific notation side. So anytime we're dealing in scientific notation, times 10 and then this little space right here, that is going to represent my exponent, which is going to tell me the number of places that I need to move. Let's spread that out a little bit. That I need to move my decimal. Okay, so that's what the exponent represents. The number of places to move the decimal. Now, we'll get to whether it's positive or negative at the end. Let's now look at what comes before the times 10. Over here on the standard notation side, when I look at this number, 8 million, I have one sig fig, and it is just the number 8. When I look at the second example, 8,350,000, this has 3 sig figs, and they are 8, 3, and 5. When I look at the last example, I have 0.000636. This has 3 sig figs, and those digits are 6, 3, and 6. So now let's compare the standard notation to the scientific notation. I have one sig fig, and it is an 8. I have an 8 in front of the times 10. I have 3 sig figs, and they are 8, 3, and 5. I have 8, 3, and 5 written before the times 10. The same thing for the last example. My sig figs, 6, 3, and 6 are the numbers written before the times 10. So what goes in front of the times 10 in my scientific notation is going to be all of the significant figures. So all significant figures will go here. Now you may have also noticed that there is a decimal point in the bottom two examples. And this is going to be the proper way to write something in scientific notation. So if you are being asked to produce an answer in my class and you are expressing that answer in scientific notation, the proper format will be like this. If you have more than one significant figure that needs to go before the times 10, you will place the decimal point after the very first sig fig. So technically, if I really wanted to, I could have come over here and said 8 point. It wouldn't have changed anything. It's still just an 8 times 10 to the 6th. But if you'll notice on the next example, it's 8.35, 6.36. So we're going to do one digit, and then we're going to put our decimal in the event that we have more than one sig fig that is going in front of the times 10. So some number, then a decimal, and then we would write however many additional significant figures are necessary. Okay, so that is the proper way to express your answer in sig figs. Now, the last thing that we need to discuss is whether a value for my exponent is positive or negative. We are going to know if something is positive or negative based on the direction that that decimal has been moved. Now, there's a variety of ways that we can explain whether it should be a positive for this case and a negative for that case. And lots of different teachers have lots of different ways of explaining it. I want you to know up front that you are going to be asked to take numbers that start in scientific notation, and you're going to produce what that answer is in standard notation. You are also going to be asked to take a number expressed in standard notation, and you are going to produce the scientific notation. So because I'm asking you to go both directions in our scientific notation format, I'm going to be very careful about how I explain whether things are positive or negative. So first, let's just say positive and negative is going to tell me the direction to move the decimal. Okay? Now, how do you know what direction to move it? I'm going to say it this way. If the value in standard notation is a very large number, then it is going to be a positive exponent. If in standard notation the value is a very small number, aka a decimal, then it's going to be a negative value. So looking at the examples we have here on the screen, we have a positive 6 for the first two examples. We have a negative 4 as our exponent for the last example.